Hi everyone. In this video we will talk about diffraction of light. In many ways diffraction is very similar to the double slit interference that we talked about before. In the case of double slit interference, what we noticed was that there were two sources of light, two secondary sources of light, the two slits, and the light from these two sources appeared on the screen with along two different paths. And so there was a path difference which generated a phase difference between the two rays of light. And so when the two rays of light that had slightly different phases interfered, they formed a pattern on the screen. It turns out the same exact thing happens for even a single slit because of the finite width of a slit. Now, because the slits have a finite width, they are really multiple sources of light built in inside, secondary sources of light, right? So now you can think of two rays of light from this single, big slit over here. There are two rays of light, or actually three rays of light that are coming in over here in this picture, and all of these have slightly different phases. And how do I know they have slightly different phases? Well, their paths are slightly different. If I draw perpendicular from this first line to the second line, you can see this one has traveled slightly more, and this third one has traveled even more, right? Because of that path difference, there's a phase difference between these two rays of light. So the amplitudes of these rays when they are incident on the screen are going to interfere, and this interference will result in either a destructive or constructive interference or somewhere in the middle, and so we are going to see a pattern. And that's basically the idea of diffraction. Now, in case of single slit diffraction, we can sort of treat this single slit as a collection of point-like sources of light themselves, secondary sources of light, right? But one thing to notice, and this is different from interference, is the fact that there's a continuous distribution of sources. In the case of the double slit interference pattern that we talked about, there were only two sources. So it was a discrete number of sources. Here we have a continuous number of sources, and we are going to add the contribution to the amplitude at the screen for each different source. And because we're going to add all of these together and it's a continuous distribution, the easiest way of doing that is using calculus, or in particular using integral calculus. So what we're going to do is we're going to say that there is a tiny little source of width dy at a distance y from the center of the slit, and we would like to find how much the amplitude that it contributes to this point P where the pattern is formed on the screen. So in order to do that, we can just simply write the electric field, because electric fields are what are getting added up. So for that particular source at y, it will be E0 times sine of omega t minus kx plus delta, right? But if I notice that at that kx part, that kx is not the same for all these different rays. In fact, it depends on how far away from the center of the slit you are. So I'm just going to call this EY, and note that this KX really is KX plus some K times delta X, where this delta X is the path difference between the ray that is coming exactly from the center and the ray that is coming from the source here located at a distance y from the center. So what is that delta x? Well, we did this before. If this angle is theta, then we know that this angle over here must also be theta. So delta x is equal to a times sine theta, or actually in this case it is just y times sine theta. Y is the distance between the two slits. So sort of let's take a closer look over here at this. How did we arrive at this? If you think of two different sources, and let's say that this is the middle, right? That's the midpoint. And for now, ignore what is written on this diagram. This is the middle, and this distance is y, okay? Then this, and since this angle is theta, then this part here, from here to the dashed line, that part is the path difference between the two rays. So that path difference shows up as y times sine theta. That's the idea. Okay, so now if we plug all of that back in, we find that EY becomes equal to E0 times sine of omega t minus kx plus delta, and this will remain no matter what value of y we choose, but then we have a part that looks like negative 2 pi over lambda times y sine theta. And what I just did here is an additional step where I just put in k is equal to 2 pi over lambda for this last bit, right? So we just plug that in over here. Okay, so this is the electric field for one source of light that is over here, but we have multiple sources and they're all continuously distributed. So we have to add the contributions all together. And so in order to add those contributions, we're simply going to integrate over y. So we get Ey dy, and we have to integrate from negative a over 2 to a over 2, because if you think about it, if that's the midpoint and the slit width is a, then this distance is a over 2, negative a over 2, and the distance all the way to the other end is a over 2. And that's the idea. So Ey dy. So this is going to give me E net. But what we are interested is not in an electric field times a length, because dy is a length. So really what we are interested in is an average electric field. So we should divide by the slit width itself, or the integral of dy, which should give you a, right? So that's the net electric field that we are seeing at the screen. So now we are going to perform this integral to actually calculate the net electric field. And the reason why we are doing it is because at the end of the day, we are interested in finding the intensity on the screen, and that screen intensity is proportional to the square of the amplitude of the electric field. So if we can find the net electric field, from there we can figure out the intensity of the interference pattern that's gonna, or the diffraction pattern in this case, that's gonna form on the screen. So let's go ahead and try to do this integral. So we know that E net, as we found before, is equal to 1 over a times integral negative a over 2 to a over 2 Ey dy. And Ey, we know that is equal to E naught times sine of omega t minus kx plus delta, minus this quantity over here, which let's for now call delta delta. So what is delta delta? And this delta delta, of course, is a function of y. So I'm going to just indicate that delta delta y, right? So this delta delta y, that quantity is just 2 pi over lambda times y sine theta. Okay. So we're going to try to switch variables. We're going to use delta delta y as a variable instead of using y as the variable, because you see that the integral is over y, but that y is masked in all these other factors, 2 pi over lambda and sine theta. So I somehow want to make my integral a little bit tractable to do, and that will happen if we use delta delta y as our integral variable. And so in order to do that, then we have to change a couple of things. First, we have to change our integral measure, which is also this differential, the dy, right? So let's try to evaluate what dy is. So dy is going to be equal to lambda over 2 pi sine theta multiplied by d delta delta of y. And how did I get this? Well, I just looked at this equation over here and I took a derivative on both sides. So d delta delta y is equal to 2 pi over lambda sine theta times dy. That's because when I'm changing y, that's when delta delta y changes. However, I'm keeping everything else fixed. For instance, lambda is fixed and theta is fixed. And that's the idea. So you do that derivative form, and then you can take the relevant factors to the other side, and you will get dy equals lambda over 2 pi sine theta d delta delta of y. So with this idea, and let's also rename this quantity sine omega t minus kx plus delta as phi, which is our traveling phase in this particular problem. Notice that the integral doesn't depend on this phi, and so we can kind of ignore the details that is hiding inside this phi, and we can write the following. So 1 over a integral, and I'm not going to put the limits yet, but I can replace dy by this lambda over 2 pi sine theta d of delta delta y, and then ey has an e0 in it times sine of phi plus and in this case, it's actually a minus, the way I've defined it, delta delta y, right? And this is the integral that we're doing. I did not write the limits yet because now since we have changed our variables from y to delta delta y, we have to reevaluate our limits. So let's do that. So when y is equal to a over 2, that's when delta delta, which is a over 2, so y, I'm replacing y by a over 2, we get 2 pi over lambda times a over 2 times sine theta. Okay, so here the 2 will cancel, and so I will get something that looks like pi a sine theta over lambda. And so you can see that if y was plus or minus a over 2, that's just going to give you delta delta of plus or minus a over 2. And the only thing that will change is the sign of this quantity over here. It's going to become plus or minus pi a sine theta over lambda. So let's plug that back in here. So what I should be integrating from is delta delta minus a over 2 to delta delta plus a over 2. So now let's bring all the constant terms that are inside the integral out so that we can proceed with the integration. And so here notice that lambda, 2 pi sine theta, e0, these do not depend on delta delta of y. So these are really constant in the integral, right? So we can pull these out. And if I do that, I'll cleverly do that and write this as e0 over 2. So there's an e0 and then there's a 2 over here. And I'm grouping these terms in a particular way so because I already know where I'm going with this. But generally, this grouping will help. Once you've done this integral once, you start noticing what patterns you can use to group things. So e0 over 2, and then I have lambda, a, and pi sine theta, so I can group these together. So I can write lambda over pi a sine theta. And then integral goes from delta delta negative a over 2 to delta delta positive a over 2. And what is inside the integral looks like sine of phi minus delta delta of y times d of delta delta of y. Okay, so now the reason why I grouped these in the constant stuff in front of the integral, the way I grouped it, if you look at it, pi a sine theta over lambda is exactly delta delta of a over 2, right? So because of that, I made this grouping so that I could just replace this by a constant. And so let's rewrite that. So we have E0 over 2, and then I have 1 over this quantity delta delta A over 2 integral delta delta negative A over 2 to delta delta of positive A over 2, and the integral that we are performing is sine of phi minus delta delta of y times d delta delta of y. Okay, so now this integral is actually quite straightforward to do. It's just a sine of an angle times d of that angle, but there is a negative sign. So if you do this integral, sine of phi minus x dx, this integral looks like cosine of phi minus x. Okay, because now if I take a derivative of this cosine, then I'll get a negative sign, but then that negative sign will cancel when I take the derivative of the stuff that is inside, right? So that's the idea. So now if I plug this, use this idea, and I'm gonna say that we are actually doing a definite integral between limit 1 and limit 2. So this is just going to be evaluated between limits 1 and 2, right? So what that means for our present problem is that this equals E0 over 2 multiplied by 1 over delta delta A over 2 times cosine of phi minus delta delta y, where this is evaluated at the two endpoints delta delta minus a over 2 to delta delta a over 2. Okay, so let's plug in, and so we will get E0 over 2 times 1 over delta delta a over 2 times cosine of phi minus delta delta a over 2 minus cosine of phi minus delta delta of minus a over 2. Okay, so let's now use a trig relationship. We know that cosine of A minus cosine of B is equal to negative 2 times sine of A plus B over 2 multiplied by sine of a minus b over 2, right? And so if we take this equation and apply it to the sum of the two cosines over here, then what we will get looks like negative 2 of sine of, so the first term would be phi minus delta delta a over 2, and I'm adding these two together, so I'll have another phi minus delta delta. This time it's a negative a over 2 divided by 2. And I'll have another sign, so this sign would look like sine of, now I'm subtracting, so if I subtract, the phi's will cancel, right? And I'll only have the remaining left over, and I'm subtracting a minus b, so this minus that, so I'll get delta delta of negative a over 2 minus delta delta of a over 2 divided by 2. The phi's have already canceled, right? One more thing to notice is that, remember, delta delta of a over 2 and delta delta of negative a over 2, these have opposite signs, right? As you can see over here. Because they have opposite signs, when I add these two together, they're just going to cancel with each other. So what I get from here looks just like 2 times sine of phi multiplied by sine of delta delta of a over 2. And this happens because, again, the delta delta of negative a over 2 has an overall negative sign, so I can pull those two signs out, so that'll cancel with the sign over here. And the 2 will cancel because there are two of these terms, so this will become 2 times delta delta over of a over 2, right? So that's the idea. So now I can take this and plug this back into my original expression, and so I get E net, the net electric field, is equal to E naught over 2 times 1 over delta delta of a over 2 times 2 times sine of phi. I'm going to plug that phi back in. What was our phi? Phi was this quantity over here, omega t minus kx plus delta. So let's plug that back in here, omega t minus kx plus delta times sine of this quantity delta delta of a over 2. And this is it, right? So these 2's will cancel. And so notice that the amplitude part of this, so let me write this electric field one more time. So this is E0 times sine of delta delta A over 2 divided by delta delta A over 2 times sine of omega t minus kx plus delta. Of course, the second part, the sine of omega t minus kx plus delta, tells you that this is a traveling wave, and this first part, that's the amplitude, which means the intensity, since that's proportional to the amplitude square, the intensity is just going to look like I equals I0, which is coming from the E0 squared, times sine of this quantity delta delta A over 2 divided by delta delta A over 2 whole squared, where delta delta of A over 2 equals pi a sine theta over lambda. Now let's look at the consequences of this intensity expression that we just found. So I'm going to rewrite the intensity expression slightly differently. I'll write it as I equals I naught sine of psi divided by psi squared. And this psi is just what I was calling delta delta of a over 2 earlier. So that's equal to pi a sine theta divided by lambda, right? So what goes on? So let's first try to investigate what happens when I change psi. And how does psi change? Well, pi, a, and lambda, these are fixed quantities, but theta will change. And how does theta change? Well, if you look at this left-hand side figure over here, as you go from one point to another on the screen, this theta will change. So as theta changes, psi will change, and hence the intensity will change, right? So let's try to figure out how this intensity changes. One way of doing that today is you can just go to a computer and ask it to plot this function I0 sine psi over psi squared. Okay, but let's try to think about it before we get into plotting this function. Well, what would happen if I set psi to 0? you immediately notice that this is a 0 by 0 form, so it's harder to calculate it. So what we are gonna probably use is this rule called L'Hopital's rule. And using L'Hopital's rule, you can actually take a derivative of the numerator and denominator and figure out that sine psi over psi, the limiting case, psi goes to 0, sine psi over psi is just equal to 1, which means that theta equals 0 will give you I equals I0. So that's a maximum. So theta equals 0 will give you a maximum, because now if you think about it, as psi increases, this stuff within the brackets can only decrease, and sine psi cannot ever be larger than 1, right? So as psi increases from 0, this quantity is going to get smaller and smaller. So this is clearly the maximum intensity, max intensity, right? So at the center of the screen, in the case of diffraction, we get an intensity maximum, right? So right at the center of the screen, somewhere over here, right, we'll get an intensity maximum. And as we go further and further out, this intensity is gonna drop in size, okay? Now let's think about what happens if psi was equal to, let's say, some integer multiple of pi. So let's call psi equal to m pi and plug that back in here. So if I plug in psi equals m pi into this equation, then what is sine of m pi? Well, we know that if m is an integer, so m is an integer plus or minus 1, plus or minus 2, etc., then sine of m pi must be equal to 0, which means that the intensity must be equal to 0. Okay, so, and 0 intensity is clearly the minimum intensity. Intensity cannot be any smaller than 0, right? Intensity is always a positive quantity, so it has to be 0 or larger. Okay, so then we have sort of an idea of what's going on. If this is my screen and this is, let's say, theta equals 0, there's a maximum here. And then somewhere over here, when theta becomes equal to pi, or theta becomes equal to, let's call this negative pi, and this one theta equals pi, there is a minimum. Okay, in between, the curve is clearly going to fall like this, so it's going to be like that. And then again, we know that at theta equals 2 pi, as we said before, theta equals 2 pi, and theta equals negative 2 pi, the value is going to again be equal to 0, right? But in the middle, this function is going to rise, but we know that it can't rise all the way to 1 because as psi increases, this intensity is actually increasing. So there'll be maximas that look like this. There'll be maximas that are smaller in size than the central maximum. Okay, and this is what a diffraction pattern, a single slit diffraction pattern looks like. Okay, so single slit diffraction pattern, that's what it looks like. And as we go on and on with higher and higher values of theta, the curve will continue, have further minimas and maximas, and the maximas will slowly decrease in size. And that's the idea. What we have to know from here, though, is what is the path difference that causes psi equals m pi? And that's pretty easy because we can just plug this psi equals m pi condition to our definition of psi. So we have psi equals pi a sine theta over lambda. So condition for minimas, right? Minima of diffraction. So minima of diffraction is pi a sine theta divided by lambda is equal to m pi. And so now if I, where m is not equal to 0, but m is equal to other integers, plus or minus 1, plus or minus 2, etc. Right? Dot, dot, dot. So now I can cancel the pi's from both sides, and then that will give me a sine theta is equal to m lambda, where m is not equal to 0, but other values of integer m are allowed, plus or minus 1, plus or minus 2, etc. Okay, and this is the condition for minima of diffraction. Okay, and we can use this directly, this formula a sine theta equals m lambda, where a stands for the width of a slit, lambda is the wavelength, and theta is the angle made relative to a horizontal line to the point where we are looking at the diffraction minimum, right? Although I have derived this relationship for a single slit, turns out that for multiple slits, these diffraction formula that we came up with, and the interference formulae that we had come up with earlier, these conditions for interference that d sine theta equals m lambda for brights and d sine theta equals m plus half lambda for darks, these still apply. So now we can generalize all of this stuff that we have learned, and we can sort of give three formulae that we can use. So let's summarize what we have learned so far about interference and diffraction. And we've learned this for diffraction, we did only a single slit, and for interference, we did just two slits. But it turns out that if we have n number of slits, that will combine both interference and diffraction. And the formulae that we found turn out to be exactly the same. So for interference, whenever interference happens, interference will happen because of the parameter d, which is really the slits separation between any two consecutive slits, okay? And the conditions would be maxes or bright happens when d sine theta is equal to some integer multiple of lambda, and let's call this MMI. So here MI, the I represents interference, so MI will be 0, plus or minus 1, plus or minus 2, etc., any integer number. And then the other condition was minimas, or darks, dark spots. And for dark spots, d sine theta has to be a half integer. So a way of writing that half integer is to say mi plus a half lambda, so that whenever mi is still an integer, mi plus half is a half integer. So these are the two conditions for interference. Interference will happen due to rays of light interfering from two different slits, and it can happen for a multiple number of slits as well, not just two, right? So that's interference. And then the second part that we have is diffraction. And generally diffraction will happen for this parameter A, which is slit width. So if there is a slit width, that will contribute to diffraction. And so for diffraction, we have learned the minimas, how to calculate the minimas, which are the diffraction minimas are the darks, intensity equals 0. So that happens when A sine theta is equal to m lambda, but we'll call it md. The d will stand for diffraction. And note that md is not equal to 0, but md is equal to plus or minus 1, all other integers, all non-zero integers, plus or minus 1, plus or minus 2, etc. Right? And what happens when md is equal to 0? So that's actually a max. And in fact, we'll call it a central max. Central maximum. That will happen when md is equal to 0, and also this implies that theta is equal to 0. So right at the center of the screen, on the other side of the slits, you'll get a maximum, and we'll call that the central maximum, which will happen for md equals 0 or theta equals 0. Okay, so that's sort of the summary information for what we have learned about interference and diffraction. I hope you enjoyed this video. Thank you very much.